Hello everyone, welcome back to the Dempaflux channel. I am Zach Peterson. Today we're going to be talking about 10 common challenges that every design engineer faces when designing a new electronics product. We'll be looking at these common challenges from 5 different perspectives: forming a specification, working in the schematics, designing the PCB layout, building a prototype, and testing against EMC standards. We've got a lot of ground to cover in this video, so let's go ahead and get started. First, let's talk about the specification for your product. Every electronic product needs a specification. Even simple devices have to have a full specification, detailing important points like engineering requirements, functional requirements, and even the desired user experience. A specification may even detail things that are required for certain aspects of compliance, such as environmental compliance. But one area of compliance that many design engineers overlook is EMC. EMC compliance can be part of a specification, and it comes in 2 forms. The first form of EMC compliance is compliance with regulatory standards in the markets where you want to sell your product. Countries around the world have different EMC standards that apply to different types of products, and it's your job as the design engineer to understand what those standards are and how they're going to impact your engineering requirements for your new product. For example, if you plan to sell your product in the United States, you will need to make sure you get a hold of the FCC rules that govern your particular product. These are codified in US law, and they can be accessed freely from the Federal Register. Another important aspect of EMC compliance that becomes part of your product specification is compliance with industry standards relating to EMC. While industry standards relating to EMC are not necessarily legal requirements per se, they are important for determining interoperability between different products destined for the same market. Product-level EMC standards in various industries can also provide safety requirements for your device. For example, IT and networking equipment, medical devices, and designs going into aerospace systems all have safety requirements which are part of EMC standards. Before you start designing any circuits or schematics, make sure you review these EMC standards and understand how they're going to drive your design process and your design decisions. Once you've formalized a specification for your product, you can start designing circuits and schematics. Your schematics are where you start implementing EMC control measures like filters, shielded components, a grounding strategy, and circuit protection. Once you understand your EMC requirements in your circuits, you can implement these control measures early. For example, do you need protection from ESD or transients? Do you expect a lot of noise on power lines, and will you require filtering? Do you have circuits operating at fast edge rates, like switching power supplies? Each of these situations is going to require a slightly different approach in circuit design, and if you understand your EMC requirements, you can address these circuit design problems early. The other challenge in schematic design and circuit design is in component selection. If you're familiar with parasitics, then you know that not all electronic components are created equal. If you select components for your circuits without considering these deeper specifications and the parasitics in your components, you're at risk of building a device that doesn't pass EMC testing. By addressing these concerns early, you can eliminate the risk of a failed prototype run and get to market faster. Once your schematics are designed and everything is reviewed and finalized, it's time to move on to the PCB layout. Even if your circuits are designed perfectly, the PCB layout can still create EMC compliance issues. 2 of the most common challenges in PCB design relating to EMC are stack-up design and grounding strategy. And in fact, the 2 are interrelated. The easiest of these 2 challenges to solve is grounding. In most designs, the easiest approach and the most effective approach from an EMC and signal integrity standpoint is to use a single ground plane for all the circuits in your design. This need for a ground layer becomes a core driver for stack-up design in modern electronics. And despite the uninformed statements about the excessive cost of multi-layer PCBs, it is mandatory in some designs to have at least one ground plane in the PCB stackup. Many designs will simply not function electrically or pass EMC without it. Once you start dealing with galvanically isolated devices or systems with a chassis ground or earth ground, incorrect connections between all these ground nets can create EMI problems or lead to EMI susceptibility. This is where you have to go back to your specification to determine the appropriate approach to prevent EMI problems. For example, in isolated DC-DC converters, we often connect the grounds on each side of a transformer using a safety capacitor. In another example with shielded connectors, we might want to have a chassis-like guard ring around the perimeter of the PCB to draw ESD away from your sensitive components. First, determine the problem you're trying to prevent based on your specification, and then approach the grounding strategy based on the type of circuitry you've included in your system. Once you've received your prototypes, they will need to be tested both functionally and electrically. This could include product-specific tests or industry-specific tests that are detailed in your device specification. One of the challenges relating to the other areas we mentioned is evaluating whether your grounding strategy was actually effective. What sometimes looks perfect in a PCB layout simulation may end up failing due to incorrect ground plane connections or ground net connections, inadequate via shielding, and shielding discontinuities at connector interfaces. Designers may discover that their carefully planned grounding architecture may actually not produce the right results due to high impedances in return paths and low shielding effectiveness in certain parts of the product. Another challenge is evaluating whether your PCB layout strategy was effective. Unfortunately, physical constraints and mechanical constraints can both force layout and routing compromises that can create EMI challenges in a prototype. For example, heat dissipation requirements or connector locations may require you to place circuits and route circuits in such a way that they create noise coupling issues or are subject to EMI susceptibility. Mechanical constraints might force you to route in ways that create susceptibility to crosstalk. And you may find that your ground connections were not placed in the right location and create long return paths which can create radiated emissions. The prototyping stage is the point to address these problems before taking your product into an EMC test lab. The final stage a product enters after going through its design and prototyping phases is the EMC testing phase. Many products pass pre-compliance testing but fail formal certification testing due to differences in test setup, cable configurations, and measurement techniques. The transition from an engineering lab into an accredited test facility often reveals insufficient margin that wasn't apparent during the pre-compliance testing phase. What may have seemed like adequate radiated and conducted emissions margin during pre-compliance testing suddenly proves insufficient once you get into an accredited EMC testing facility. The final challenge that develops during the testing phase is, of course, the need for quick fixes to the product. Usually when products get to this stage, I have seen companies throw every single design change they can think of at a PCB layout in order to get the product to just work. This often causes design teams who don't fully understand the root cause of their EMC problems to implement band-aid solutions that just add manufacturing and assembly costs to their final product. Rather than guessing at the source of your EMC problems, you need an analysis tool that helps you pinpoint the root cause directly from your PCB layout data. That's where DempaFlux comes in. DempaFlux is a powerful analysis platform that looks directly at your design data and helps you identify sources of EMI. DempaFlux will also generate an easy-to-read report and recommend fixes to your circuits and your PCB layout. Go to DempaFlux.com today and see how they can help you solve your toughest EMC challenges. Thanks for watching this video, everybody. Make sure to hit the subscribe button to learn more about EMC challenges in modern electronics, and I'll see you in the next video.